Hi, I'm Eric Adams, a cloud-native software engineer at Intel. In this video, I'm going to show you how to do federated learning in a more secure way using Intel trusted execution environments. Training AI models requires a lot of computational power and, more importantly, access to all of the data being trained. This becomes a challenge when different organizations possess some of the data to be trained, but they can't share it. A good example is health records. HIPAA laws prevent hospitals from sharing records. The data may also just be too large to transmit economically. OpenFL helps to address the data silo problem in machine learning. It stands for Open Federated Learning and is a Linux Foundation incubation project. OpenFL supports all popular machine learning frameworks, including Keras, PyTorch, and TensorFlow. It is distributed through GitHub, PyPy, and even Docker Hub. It is scalable, provides security, and it strives to deliver a good developer experience. The way it works, each institution agrees to a federated learning plan before starting the training. This includes relevant information like who will be taking part in the experiment, what data will be accessed during execution, and all of the code that will run on each collaborator node. Each collaborator, a node somewhere on the internet, will train using the data it has. Later in the demo, I will show you this working with colorectal cancer data. At predetermined intervals, each collaborator will update its model weights and send the weights to an aggregator. The aggregator service combines the weights from individual collaborator models to construct a global model. The aggregator will then redistribute the global model to all the collaborators, each of which proceeds to continue training, repeating the above steps until the end criterion is met. Each collaborator controls its own data, never sharing it. That is the overall concept of OpenFL. An important component in the overall workflow is the governor. It is responsible for securing the ledger and remotely attesting the aggregator and collaborator nodes that are participating in the training task in their own silos. You can think of the governor as the centralized service that brings together datasets that have no prior knowledge of each other. On the picture, you'll notice a red box and the word SGX. That box represents a trusted execution environment based on Intel Software Guard extensions. A trusted execution environment provides hardware-based memory encryption and integrity, and greater access protection, useful in protecting machine learning models and sensitive data. The important services in that box all run in trusted execution environments. With the governor established, you need one aggregator node. It is the central server in each federated learning experiment. Its responsibilities include assigning training and validation tasks for each collaborator, taking each collaborator's updated model weights and combining them into a new model at the end of each training round, and applying compression and decompression to network traffic in large federations. You will notice all of its important services are run within trusted execution environments. Next, we have the collaborator nodes. There can be many of these. This is where all of the localized training happens and is the real value of OpenFL. Each collaborator keeps their data local to their location. All of the tasks needed by OpenFL in the training happens within the trusted execution environments. All communication between collaborators to aggregators and aggregators to the governor use mutual TLS for maximum privacy. The final piece to this solution is the integration with Intel Trust Authority. This is a third-party attestation service available from Intel that is a first step in creating a multi-cloud, multi-trusted execution environment service to drive forward adoption of confidential computing. It will attest to the legitimacy of Intel SGX enclaves, as well as the software components running within. The governor uses this trust authority attestation to verify that the code and model agreed to ahead of time have not changed at the runtime. Now that you've seen all the pieces put together, let me show you a demo of it actually running. Let me show you a preview of this working. This is my OpenShift cluster. If I click on the installed operators and then click on the Intel device plugins operator, you can see that Intel provides certified plugins to enable Intel accelerators and other CPU features like Intel SGX. There is already an instance of the SGX plugin running. If I go to my compute node and click on it, I can dive into the YAMLs to see more details on this node. If I search for EPC, which means Enclave Page Cache, you first see the annotation is added by Node Feature Discovery. This labels nodes with detailed capabilities and is how the SGX plugin knows to run on this node. Further down, you can see that my node's EPC memory capacity is over 136 gigabytes. Switching over to my terminal screens, the one on the right is the script I'm about to run. Let me start the script on the left, and while it runs, I will explain what happens. The experiment register function uses the OpenFL binary called fx to set the governor URL, which is another machine in this subnet. It could be anywhere on the internet. The aggregator and collaborators are activated and each agree to a plan of who is allowed to contribute along with other parameters. Each of the datasets are registered with the governor. In this example, I am showing open source medical brain images, each with different diseases. This is the type of data ideally suited for OpenFL to improve model accuracy while maintaining data privacy, which is sometimes required by law. After everything is registered with the governor, each collaborator needs a plan ID. Each collaborator needs to vote on the plan. Once everyone has voted, you can start the federated learning. For convenience, I am using a file with common environment variables. I'm going to add the plan ID here. Using a customize, I'm going to start the collaborators and aggregator at the same time. In a typical OpenFL environment, the collaborators and aggregators would be in different locations, but for demo purposes, I'm showing this on a single cluster. Now, watching an AI training isn't all that exciting. The top window is the logs of the aggregator. It's not doing any training, but it's gathering the data from all the collaborators. The center and bottom windows are the logs of each collaborator. The pods have an init container so that it sometimes takes a moment to start the job. The container images were built using Grameen shielded containers, which builds container images with the libOS that allows applications like OpenFL to run unmodified within an Intel SGX enclave. In our current implementation, the logs warn about Grameen because this container image has debug variables injected in. You can ignore that. What is happening is each collaborator node is going to load its private data into an Intel SGX enclave. It makes sure that its local data identically matches what was specified in the plan using a hashing function. This sequence of validation on the aggregate model, training, and validation on the updated model is all done with local data. No private data is shared with any other node in the federation. This is the important value of OpenFL. Let's speed up the video to get to some important notes in the log. Here, you can see both collaborators are getting a token from the Intel Trust Authority to attest their encrypted memory enclaves. The plan ID has been registered and enclaves attested, so training on each node can begin. If you look at the aggregator logs, a model is now registered with the governor. Round 0 training will begin, and the model integrity is verified. The aggregator shows that round 0 is done. Each collaborator gets the updated model with both collaborators' weights averaged in. The second round of training on the updated model will begin. The second round of training is now done. The aggregator will update each collaborator with the second round model. Only 2 rounds of training was done on this, but it's pretty clear how OpenFL can improve model accuracy and maintain data privacy. The end of the federated training has concluded. If I log into the node and go to the /temp directory, I can see the final model and files exchanged. This temp directory is for demo purposes. In a production environment, make sure to give consideration for how you want to secure the model at rest. That was a simple demo of how OpenFL can increase model accuracy without having to compromise and share private data with other institutions. Intel Trusted Execution Technology, starting with Intel SGX and soon Intel TDX, provides that extra layer of security to better protect models as they are trained. Learn more about OpenFL at the Secure Federated AI GitHub. Intel is open sourcing the Intel SGX integration for both aggregator and collaborators. Also, the Intel Technology Enabling for OpenShift GitHub is where all of the certified device plugins for OpenShift are packaged, including the Intel SGX plugin, Intel GPU plugin, and Quick Assist plugin, and so on. All of the plugins officially supported in Kubernetes are maintained on the Intel Device Plugins for Kubernetes GitHub. Thanks for watching.